Assalamu alaikum students. Today we are going to learn assess uncertainty in derived quantity by simple addition of percentage uncertainty. So we already know what is uncertainty or simply an error. Whenever we do have a difference in measured value and the true value, we do have an error. So uncertainty means simply an error. Whenever we are going to measure something, so we must have an error. We cannot measure anything with infinite accuracy or 100% accuracy. We can never measure anything. So to measure, we need some instrument, just like we do have scale, we do have vernier caliper, we do have screw gauge, we do have digital balance, we do have physical balance, and many more equipment we do use to measure. So whenever we do measure something, we do have some error or uncertainty. Now question arises, what is absolute uncertainty? Absolute uncertainty is basically equal to the least count, and this can be calculated easily, just like you can see this scale. Okay, now in this scale you can see that the values are marked from 0 to 20. Now 0 to 1 centimeter we do have 10 divisions, just like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 divisions within 1 centimeter. So this absolute uncertainty is basically equal to the least count. And what is basically least count? Least count is minimum measurement made by an instrument. So what will be the minimum measurement or simply the pitch of this scale? We do have 10 divisions that are representing 1 centimeter. So it means that the least count will be 0.1 centimeter or simply 1 millimeter. So least count for scale, least count for meter rule or simply the ruler or measuring tape, for ruler / measuring tape / measuring tape, or meter rule, they do have the same least count. Meter rule, that is basically equal to 0.1 centimeter, or we can write 1 millimeter. This least count, minimum measurement made by an instrument, we can also call it absolute uncertainty. What does it mean by absolute uncertainty? Means this uncertainty must be present in it whenever we are going to measure it. Already we have clear one thing. Whenever we are going to measure something, so we do have an error or uncertainty. This uncertainty will be equal to the least count. Now question arises, how we could identify this uncertainty. Just like the length we are going to measure by this scale right here, and we are going to mark from its initial position right here. This is 0, we have set it 0, and this is coming till 10.5, 6, 7, 8, 9, 10, 11, 11.1, 2, 3, 4. Yes, this is coming between the 11.3 and the 4th. So the maximum possible error we do have, that is 0.1 centimeter. So this is uncertainty present in it. So whenever we are going to measure it, we do have some uncertainty. The maximum possible uncertainty, that will be equal to 0.1 centimeter or 1 millimeter. We do call it absolute uncertainty. Absolute uncertainty. Uncertainty. Okay. Question arises, do we have some absolute uncertainty for vernier caliper? We can calculate it easily. How? Least count or absolute uncertainty for vernier caliper. That will be equal to pitch over number of division on vernier scale. Number of division on vernier scale. No doubt there are two types of scales in the vernier caliper. One of that is main scale and another one is vernier divisions. So pitch means indicating the minimum distance between the two consecutive threads. Just like the two consecutive threads in the scale we do have, that is 1 millimeter, means pitch is 1 millimeter right here. But in the case of vernier caliper, the two consecutive threads are indicating 0.1, simply 1 millimeter, and the number of division present in it, that is 10. So the least count or the absolute uncertainty will be 0.1 millimeter, or simply the least count for the vernier caliper we do have, that is 0.1 millimeter, or we can also write it 0.01 centimeter. Okay. Similarly, the absolute uncertainty present or the least count for screw gauge, we can even calculate it. Screw gauge, the pitch of the screw gauge over number of circular divisions. Number of circular divisions. Now we do have the pitch in the case of a screw gauge, that is again 1 millimeter, but there are 100 divisions in it. So we do have the least count or absolute uncertainty for the screw gauge, that is 0.01 millimeter, or we can write 0.001 centimeter. So this is the procedure to calculate the absolute uncertainty. So whenever we are going to measure something, we need a measuring instrument. Whenever we do have a measuring instrument, we have some uncertainty or absolute uncertainty or the least count that could be calculated in this way. Okay, now question arises, what are the cases and how we are going to calculate the percentage uncertainty in the final reading, or assess how we are going to assess it, how we are going to solve it numerically, and what are the rules. Okay, so after that we are going to discuss this. Okay, now the first case to assess the uncertainty in the derived quantity, that is in the case of addition and subtraction. And don't get confused, we do have the same case even in the addition and even in the subtraction. Okay, so the first case we do have the uncertainty in the derived quantity. The first case is addition or subtraction. That is the rule. Addition and subtraction. The rule is same. The rule is same for addition as well as for subtraction. Now, the rule is that the absolute uncertainties are added. And question arises, how we do write an absolute uncertainty? Just like if we do have measured a length represented with L. The length we have measured, that is 3.2 centimeter. This is being measured 3.2 centimeter, which is measured by a meter rule or measuring tape. Question arises, how we do write the absolute uncertainty? The absolute uncertainty will be written as plus and minus. You will ask, why we are writing plus and minus? 0.1 centimeter. This 0.1 we have written just because least count of the meter rule of the measuring tape, that is 0.1 centimeter or 1 millimeter. And we have to represent with the same units. We do not write one of that is centimeter and another one is millimeter. No, we have to write both in the same units. Okay. Now after that, why we are writing this plus and minus? Indicating that, just like in the previous exam, previous question, I have asked from you that the length of this pencil, okay, this length is almost 11.1, 2, 3, 4, 3 and 4. So this actually lies between 11.3 and 4. The maximum error it must have 0.1 centimeter. Might be 11.3 is correct, might be 11.4 is correct. The actual reading lies between them. So that's why this plus and minus both indicate that this is the maximum possible error. Might be we can measure less than that of actual one, might be we can measure more than that of actual one. So for the less than we are writing plus, and for more we are writing minus. So both are possibilities. So absolute uncertainty is always marked with the plus and minus sign. Now question arises, we have two pencils. Okay. Likewise from the scale, okay, I will draw right here. Yes. The first pencil, this way. This is 10.5 and 6. This lies between 10.5 and 6. This pencil having length about 10.5. I have indicated. In the same way, this pencil I will draw right here. Yeah. Okay, this is the pencil I have made right here. Yes. Okay. From the starting position. Okay. We are writing it with x1. x1. And another pencil I do have. .3 and 4. It lies between 3 and 4. I do mark it. I do mark it right here. The same. .3, the second pencil, indicating with x2. 12.3 centimeter, 10.5 centimeter. Now, if you want to add these two lengths, addition, if we require addition, the total length including the two lengths, the total length for two pencils we can write as first one is 10.5, no doubt, we do write 10.5 centimeter plus minus 0.1 centimeter. Why we are writing plus minus 0.1 centimeter? Because we have measured the length of each pencil from this measuring instrument, means meter rule. Okay, so 0.1 centimeter absolute uncertainty for the first pencil. And then The second one we do have, that is 12.3 centimeter. 12.3 centimeter plus minus 0.1 centimeter. Why we are writing plus minus 0.1 centimeter? Again the same reason, we have measured the length of this pencil, the second pencil, from the same instrument, that is meter rule or the ruler, having absolute uncertainty plus minus 0.1 centimeter. So what will be the final answer? Yes, and the uncertainty. So 10.5 and 12.3, 3 plus 5, that makes 8, so 0.8 centimeter, and 10 plus 12, that makes 22, so 22.8 centimeter. What about the final uncertainty that we are asking right here? Assess uncertainty in derived quantity. So uncertainty in the final reading, that we can write as addition of individual uncertainties, addition of absolute uncertainties. So this is 0.1 centimeter and this one is also 0.1 centimeter. We do write 0.1 plus 0.1, that makes 0.2 centimeter. Yes, this is the final uncertainty in case of addition. And the rule is same. You can see that for the addition and subtraction, the rule says that absolute uncertainties are being added. Okay. Now, question arises, if we want to take the difference between the two lengths, the difference between the lengths of two pencils, okay. For taking difference, we have to subtract from the greater length to the smaller one. Which one is greater, 12.3 or 10.5? Obviously 12.3. So we do write x2 minus x1, okay, with their values. So x2 we do write 12.3 centimeter plus minus 0.1 centimeter. Why we are writing plus minus 0.1 centimeter? Because we have measured the length of the pencil from the meter rule or the ruler. Okay. Then minus x1, the length of second pencil means x1, that is 10.5 centimeter plus minus 0.1 centimeter. Why we are writing 0.1 centimeter? Because we have measured it from the same instrument. Okay, according to the rule, 12.3 minus 10.5. If we are going to subtract this, 12.3 and then 10.5, subtract it from 13. If we are going to reduce 5, so it becomes 8. And this becomes 1. So 1 minus 0 is 1. Point remains same. 1 minus 1 is 0, 1.8 centimeter. So 12.3 minus 10.5, that is 1.8 centimeter. What about the final uncertainty that we are going to assess right here? The rule is same for the addition and the subtraction. The absolute uncertainties are being added. So absolute uncertainty for individual reading, that is 0.1 and 0.1 centimeter, that is being added. So what it be? 0.1 plus 0.1, that makes 0.2 centimeter. So simple. This is all about for the addition and subtraction. The rule is same. Okay. Take the screenshot of this. Now we do have the next case. So first we have did addition and subtraction. The absolute uncertainties are being added in the final assessed value. And for the second case, multiplication and division. Okay, total we do have 4 cases that we have to discuss. The second one is multiplication and division, and the third one is power factor. Okay, then multiplication and division. So what we are going to do, we are going to measure a physical quantity that contains a formula having multiplication is being involved, or having division is being involved in it. So see right here, what will be the case? Just like we do have the question. Calculate resistance using voltmeter reading V is equal to 3.56 volt plus minus 0.20 volt. Now what does it mean by this? Calculate resistance using voltmeter. V is equal to 3.56 volts plus minus 0.02 volt, and ammeter reading as I. Ammeter basically measures the current. That is 0.3 amperes plus minus 0.1 ampere. Now what we have to do right here, we are going to measure resistance. Calculate resistance, also calculate uncertainty. And derived quantity. Now question arises, why we have written this 3.56 volt and plus minus 0.02 volt. What does it indicate? No doubt 3.56 volt is being measured value from the voltmeter, means voltage is being measured right here, 3.56 volt. Plus minus, after this plus minus, that must indicate its absolute uncertainty or simply the least count. We have just taken a random value right here, just like to understand. 0.02 volt means the least count for this instrument, that is 0.02 volt or absolute uncertainty. Minimum measurement, it can measure 0.02 volt. Likewise, ammeter reading, we do have I is equal to 0.3 ampere plus minus 0.1 ampere. So after this plus minus, we have 0.1 indicating that least count for this ammeter, that is 0.1 amperes. We have to calculate uncertainty in the derived quantity. Now how we are going to calculate it? That is much easy. Question arises, what is the rule for the multiplication and division? What is the rule for the multiplication and division? The rule says that the percentage uncertainties are added. And the rule is being same for the multiplication and division. We have written just like we have done for addition and subtraction, the rule is being same. Likewise, multiplication and division, the rule is being same. Now question arises, how we do calculate this percentage uncertainty? That is much easy. Okay. Percentage uncertainty, having the formula. Percentage uncertainty, having formula. What is that formula? Percentage uncertainty is equal to absolute uncertainty. Absolute uncertainty over measured value or reading. Measured value. No doubt, you can even replace this absolute uncertainty by least count. Multiply by 100%. This is the formula. And measured value, you can also write reading, whatever the reading that you have taken from the measuring instrument. Clearly, in the beginning of the lecture, I told you that any measurement that we do measure, first thing that we do use instruments, devices. The second thing is that we can never measure the reading with 100% accuracy. There is uncertainty, and this uncertainty we are calculating right here in different cases. Okay. Now absolute uncertainty for that specific instrument, just like we have measured the length by the rule, the meter rule or the measuring tape, we do have the absolute uncertainty will be 0.1 centimeter. For the 1 year caliper, we do have 0.01 centimeter. And for the screw gauge, we do have 0.001 centimeter. Likewise, we do have some uncertainty in the final reading. So, we have to calculate percentage uncertainties of each measurement, and then we have to add it. Not to worry about that. We are going to discuss in detail in examples. Okay, so percentage uncertainties are being added, so we can get the percentage error is being there. Percentage uncertainty is being this, so we can calculate easily by calculating that amount of percentage, the uncertainty in the final reading. So the formula for the percentage uncertainty, we do have this one. Okay. Now, question arises, what is the relationship for the resistance using this voltmeter reading and this ammeter reading? Okay. What is the relationship for the resistance? We all know that resistance is the property which opposes the flow of electric current, or the ratio of voltage to the current is called resistance. What is the formula? First we do calculate the resistance and then its uncertainty in the final reading. See right here. The resistance we can write R is equal to V over I, no doubt. First we do calculate the resistance and then we do talk about its uncertainty in the final assessed value. So voltage value we do have, that is 3.56. We do write 3.56 over I. I we do have, that is 0.3. 0.3. Now after dividing it, 3.56 with 0.3, we do have, yes, here we do have the calculator, 3.56 divided by 0.3, we do have 11.86 ohms resistance we have calculated. Okay. Now question arises, what will be the uncertainty in the final value? Means we have calculated this value, but what is the uncertainty in the final value? Rule says that the percentage uncertainties are being added. Either they do divide, either they do multiply. The rule is being same. So what we will do, in the first step we do calculate the percentage uncertainty. Where we have measured by the two sources, from where the voltage from the voltmeter, and the second source is the current from the ammeter. These two sources are being used right here, that's why. If we do have third any other source, that is irrelevant, so we do not discuss that. Just like resistance is dependent on the voltage and current. And if they will give any other irrelevant thing, so we do not use to calculate their percentage uncertainties. We are just going to calculate the percentage uncertainties of those quantities which are being involved in the measurement. Okay. The first thing, voltage is being involved and current. So voltage, the percentage uncertainties we do calculate. First we do calculate the percentage uncertainty for the voltage. Yes, from here. Percentage uncertainty for voltage of voltage. That is, what is the formula? Absolute uncertainty divided by measured value multiplied by 100%. Yes. What is the absolute uncertainty for the voltage? 0.02. Randomly, we do have different kinds of voltmeter. Not to worry about that. We do use 0.02. If we do have any other instrument, whatever be the least count indicated there, we can use that one. Okay. If it is DMM, it will be different, 0.001. If it is being analog, it may be different. Okay. So just for an example, we have taken 0.02 volt. So absolute uncertainty for the voltage, we are writing 0.02 volt. The unit must be same for the numerator and the denominator. Okay. Otherwise, you have to first convert it and then divide it. The units are being cancelled out right here. So the value or the measured value of the voltage, that is 3.56. Okay. We do have the reading. We do have the percentage uncertainty for the voltage, that is 0.02 divided by 3.56. 3.56. Okay. After dividing it, we do have 0.0056 multiplied by 100. Multiplied by 100. We do 0.561. So we do write 0.56%. Okay. So this will be the percentage uncertainty in measurement of the voltage. Now percentage uncertainty for percentage uncertainty of current. Again, we need absolute uncertainty for the current. We need measured value multiplied by 100%. So, what is the absolute uncertainty in the case of measuring current by the ammeter? Absolute uncertainty will be 0.1. 0.1 divided by the measured value by the ammeter, that is 0.3. So 0.3. After division, we can write 0.1 divided by 0.3. We do have 33.33%. 33.33%. According to the rule, what we have to do, percentage uncertainties are being added, and this rule is being same for multiplication and division. So percentage, we are going to add percentage uncertainty of voltage plus percentage uncertainty for current. We do have 33.33 and another one is 0.56%. So 0.56% plus 33.33%. So it will be 33.33 plus 0.56. It will be 33.89%. Okay. The percentage we have calculated right here, 33.89%. Now, resistance value we have calculated, that is 11.89 ohms. So the final value that is being fluctuate, or the final value having an error or uncertainty, that will be 33.89% of this. So first we do calculate 33.89% of 11.86 ohms. So the uncertainty, we can calculate it easily. Of means multiplication, so 33.89% means divided by 100. Percent basically derived from percentum, divided by 100. Of means multiply, 11.86 ohms. Yes, 33.89. 33.89 divided by 100, we do have 0.3389 multiplied by 11.86. Yes, we do have 4.019 ohms. So we do write the resistance finally as 11.86 ohms plus minus 4.019 ohms. Now most of the time in CIA they will ask to have the final answer up to appropriate number of significant figures. We must know what are the rules to have the significant figures. You can view my previous video or detailed. We have discussed on the significant figures, what are the significant figures and how we do round off. Here we are going to just identify that final result having appropriate number of significant figures. So how we do calculate it, or how we do convert it, how we do round off it. So see right here, the two values we do have, just like reading and their uncertainty. For dealing it with reading, we have to see all the readings. Means just like for the voltage and for the current, we do have the reading 3.56. How many significant figures are there? Three significant figures. And for the current, how many significant figures are there? Two. Only one significant figure. Okay. Now, how we do write the final answer to appropriate number of significant figures? We do find the least number of significant figures. So in the given reading, we do have the least number of significant figures, that is one significant figure. So if we do have one significant figure, so we have to write in two significant figures. The least one we have to find. And we have to convert that, the final reading, into the least number of significant figure in the given data. In the given data, we do have three significant figures and one significant figure, means the one is the least one. So final reading, if it is other than one, so we do write the least one. Okay, just like one of that is the data is three significant figure and another one is two significant figures, so we will convert the final answer into two significant figure, or one more than that, means three significant figures. And if the given data having three significant figure and one significant figure, so instead of one we have to write it two significant figure. So this is the exceptional case for the one that we have to write it into two significant figures. So just we need to locate the least number of significant figures. Mostly we do this except one situation. Okay? If we do have one significant figure, so we do convert it into two, and if we do have the least number, that is just like three significant figure and two significant figures, so we do convert it into two significant figures. Just like if we do have the given data having four significant figures and three significant figures, so the least one is three, so we can write the final answer into three significant figures. Okay, so right here, due to this one significant figure, we do write the final answer into two significant figure. So the large digit is more than 5. What we will do? We have discussed in the previous video for the significant figures. Clearly we have identified if the large digit is more than 5 and we have to round off. So what we will do, we will add 1 to the retained digit. So it becomes 11.9. And again, we have to convert it into two significant figures. So the large digit becomes this and we have to transform into two significant figures. So So last digit is more than 5. So we will add 1 to the written digit. So it becomes 12.0. Again 12.0 having 3 significant figures. So we have to write the final answer into 2 significant figures, that is 12. So 12 ohm. 12 ohm, okay, that was for the measurement, for the resistance, okay, no doubt. But we have to discuss for the uncertainty. For having uncertainty, we will look for uncertainty, just like voltage having uncertainty, that is 0.02, one significant figure. One significant figure. And again 0.1 having one significant figure. Okay. So the final answer we have to write in one significant figure for the uncertainty. Just like this is 9, more than 1, more than 5, so 1 will be added right here. So no doubt it becomes 4.02. And then even it is having the 3 significant figure, we have to convert it into 1. So 2 simply drop because it is less than 5, and then 4.00, 4.0, and furthermore it is having 2 significant figure. We can convert, we can write the final answer into one significant figure as 4 ohms. So 12 ohm plus minus 4 ohms, that will be the resistance with uncertainty, with uncertainty, with uncertainty, with uncertainty, S. Yes. In this way. Okay, this was the same case for the division we do have. We do more practice, don't worry about that. Now we will move to the power factor. Third case we do have, that is power factor. Power factor. Power factor. What does it mean by this power factor? It means the physical quantity that we are measuring right here, having the formula involving a power, just like volume of a sphere. Volume of a sphere is 4 over 3 pi r cube. R, we do know that radius. Mostly we do measure the diameter. Okay, so it's better to write d over 2 cube, d over 2 cube, although we know that radius is half of the diameter. More simply we can write 4 over 3 pi d cube over 8, 4 1 the 4, 4 to the 8, that becomes pi over 6 d cube. Yes, the volume of the sphere is pi over 6 d cube. Now question arises, if we do have the power factor involved, so how we do deal with that situation? Okay, now the volume we have to measure right here, pi over 6 d cube, just like the question we do have. First we are going to tell you the rule. Okay, in case of power factor, in case of power factor, in case of power factor, percentage will be multiplied with power factor, with power factor. Okay, so see right here how we do deal with this situation. Okay, let we have the question, calculate volume of a sphere or ball. There is no difference between the ball and the sphere. Calculate the volume of ball with uncertainty, with uncertainty, with uncertainty. Okay. Now, the given data, calculate the volume of the ball with uncertainty, the diameter. Now the data is given. The diameter the diameter of ball measured by vernier caliper as 3.25 centimeter. Okay, so we have to calculate it, and nothing given right here what is the absolute uncertainty. You must remember the uncertainty or the absolute uncertainty or the least count for the vernier caliper, that is 0.01 centimeter. So the diameter we do have, that is 3.25 centimeter, and we do write plus minus how much? 0.01 centimeter, because we know the least count or the absolute uncertainty for the vernier caliper is 0.01 centimeter. Question arises how we do deal this volume. We know the formula, V is equal to pi over 6 d cube. Okay. Pi is a constant, 6 is a constant, so we only deal with d. Okay, now we need percentage uncertainty in the first step. Percentage uncertainty for diameter d. We do have the formula, that is absolute uncertainty over measured value multiplied by 100%. The absolute uncertainty is 0.01, so we do write 0.01 centimeter. The unit is already same, otherwise we do convert it to have the same units. Then the reading we do have, that is 3.25 centimeter. Okay, now we will calculate the percentage uncertainty in this situation. 0.01, 0.01 divided by 3.25, that is 0.003, and the percentage will be 0.30%. So percentage uncertainty in D, we do have this. What is the power involved right here? Power factor for the volume of the ball. We do have power involved only in D. Okay, so D having power 3. So what we will do according to the situation, that we do multiply percentage uncertainty with the power factor. So percentage uncertainty multiplied by power factor. Okay, what it be? Percentage is 0.3%. Multiply by power factor is 3. Final answer, 3 multiplied by 0.3, it will be 0.9%. So overall percentage error we do have, that percentage uncertainty will be 0.9%. So 0.9% of the volume. First we do calculate the volume. What is the volume measured? Pi divided by 6 d cube. So pi having value 3.14 divided by 6, diameter is given 3.25. It's cube with centimeter. Unit is mandatory to recognize what will be the final unit. So 3.25 cube, 3.25 cube, 34.32 multiply by 3.14 over 6, 3.14 over 1 4 over 6, 0.5233. Okay, so final answer will be 17.94 centimeter cube with uncertainty means plus minus 0.161 centimeter cube. Question arises, what will be the final answer with the appropriate significant figures? So if we do see that given data is having three significant figures, 3.25, so this is the only one thing, means only case we do have only one given quantity. So we do see that three significant figures, so final answer we do convert into three significant figures. So 17.944 is less than 5, so we do simply drop it, and 17.9 centimeter cube will be the final answer. And if we do see the uncertainty is also given from the single source. The single source is 0.01 centimeter, means one significant figure we do have. So we can write the final answer in the one significant figure. One is less than 5, so simply drop it. Then we do have 6, so 6 is more than 5, so we do add 1. Final answer will be 0.2 centimeter cube. So this is all about the power factor. I do summarize again. In the case of power factor, we do first find out the percentage uncertainty, and then power factor will be multiplied with that percentage uncertainty, and then we do calculate this percentage to the measured value of the given quantity, means volume we have to measure. So volume comes out to be 17.9, so we do measure the percentage. Instead of 0.3 we have multiplied with 3, so it becomes 0.9%. so 0.9% of 17.94 is 0.161, and then we have converted into one significant figure, because the given data having uncertainty with one significant figure, that is 0.01 having one significant figure. Okay, now we will come towards the questions as they have given in CIE or AKU. The same topic is being present in AKU as well as in CIE, so we have to deal with the same. Okay, now we will move to the questions or the examples. Okay, okay, we do have the question in CIE MJ May June 18 May June 18 paper 2-3 question number 1. Paper 2-3 question number 1. So this is the question in CIE results. Question is, the potential difference across a resistor is 5 volt, 5.0 volt plus minus 0.1 volt. So already we know that this plus minus and 0.1 volt written, so it means that it is the absolute uncertainty of the voltage. The resistance is given 125 ohms plus minus 3%. So percentage uncertainty is given right here. Calculate power dissipated. Calculate power dissipated. We have to calculate, and the second part, calculate percentage uncertainty and power dissipated, and write the power with uncertainty with appropriate significant figures. So power having three formulas. Question arises, which formula we do apply? Electric power is P is equal to V into I. No doubt P is equal to W over T. W over T means the rate of doing work is called power. But nowhere the work done is given, no, and even the time is not given, so we do not apply that formula. Even these formulas are being derived from the same rate of doing work, means W over T. For this also to have P is equal to V into I. The second possible formula for the power is V square over R. And the third formula for the power, that is I square multiplied by R. Which formula we do apply? We do have the data having the voltage and the resistance. So which formula we do use? Obviously we cannot apply this one. It is having current and the resistance. Obviously we cannot apply this one. Voltage and current. We don't have both things, means voltage and resistance we do have, so we do not apply this one. But we do apply this one, V square over R. And again power will be involved in it. So this formula we are going to use. In the first part, we have to just calculate the power dissipated. P is equal to V square over R. V means voltage is given 5.0, so 5.0, it's squared over the resistance. Resistance we have 125. No need to locate the percentage or absolute uncertainty for only the calculation of the power. In this case, the percentage uncertainty we do deal with absolute uncertainties, but in the first case there is no need to see the absolute uncertainties, only the reading we are going to deal. So 5.0 whole square 125 over 125 means it becomes 25 over 125. So 25 over 125. This will be 0.2. So 0.2 watt. Power is being measured in watt. If all the units are SI, just like volt and ohm, they both are SI, so we do get the unit of power will be watt, SI unit. Okay, 0.2 watt exactly. Now calculate percentage uncertainty in power. Percentage uncertainty, he is not using the term calculate the final uncertainty. So what we will do, we will just calculate the percentage uncertainty as he has required. So percentage uncertainty in power means we do deal the percentage of V and percentage of. Here two cases are being applying. We do have the two cases. One of that is division and another one is power factor. What is the situation of power factor? We have learned in the previous example of volume that pi over 6 dq. So we do multiply the percentage uncertainty with the power factor, that was 3 in that case. And here the power factor is 2, V square over R. So first we do calculate the percentage uncertainty for the voltage, then we do multiply with 2, and due to the division, we do calculate the percentage uncertainty in the resistance. That is already given right here, no need to calculate it. And then we do add them to get the total percentage uncertainty. So he is asking right here, calculate the percentage uncertainty in the power. Okay, so what we will do for that, the percentage uncertainty for the first case, V squared. First we do calculate for V and then we do deal with V squared. So for V, the percentage uncertainty we can calculate easily. Okay, percentage uncertainty means absolute uncertainty over measured value multiplied by 100%. Absolute uncertainty for the voltage we do have 0.1 or the least count. The unit must be same. Both are in volts. And the measured value is 5.0 volt. They are being cancelled easily. Now we do divide and then take the 100%. So 0.1 divided by 5.0. We do have 0.02 multiplied by 100, that becomes 2%. Overall answer will be 2%. Okay, but we have to calculate the power factor as well, because we can see the formula of power V square over R. There is a power factor for the voltage. So due to the power factor, we have percentage will be multiplied, percentage of V multiplied with the power is 2. So power factor means power factor. First we do add power factor, then we do replace the value. Power factor is 2, percentage of voltage is 2%. So we do have percentage in V square, percentage in V square, percentage uncertainty, that is 4%. Okay, but we don't have only the voltage, we do have the resistance, and here the benefit they have given, that is directly they have given the percentage. No need to calculate it. Whenever the data, The benefit we do have right here, already they have given the percentage for the resistance, no need to calculate it. So what we will do, the total percentage uncertainty, will be percentage uncertainty in V square plus percentage uncertainty in resistance, okay, that will be 4% plus 3%, that makes 7% overall. Now finally, in the third part, they are asking, and this contains 2 marks. Here they have allocated 2 marks for it, and even they have assigned 2 marks for the calculation of power, and they have assigned 2 further marks for this portion. So it means that they have given 6-mark question. Okay, that is much easy. Now write power with uncertainty in appropriate number of significant figures. So first we have to calculate the 7% of the measured value for the power, that is 0.2 watt. Okay, so 7%. First we define the uncertainty in the power, that is 0.2 watt plus minus the percentage uncertainty for the 0.2 watt. The percentage, how much percentage we need? The total percentage error or uncertainty is 7%. 0.2 watt multiplied by 7%. So 0.2 watt plus minus 0.2 multiplied by 7 is 1.4, because 7 to the 14. So 0.2 multiplied by 7 will be 1.4%, or 1.4 over 100. So in watts, 0.2 watt plus minus 1.4 over 100, that will makes 2 decimal place at the back. So 1, 4. So 1, 2. So 0.014. 0.014 watt. Okay. Now we have to write the final answer into appropriate significant figures. So given data, here we do have 2 significant figures in the reading. Here we do have 3. So final answer will be converted into 2 significant figures. Okay. So 0.2 we do have. So we do write into 2 significant figures as 0.20 watt plus minus. So final answer having 1 significant figure, because 1 significant figure is the least number of significant figure in the given data of uncertainty. Okay. Now we will move to the next question. Okay. So previously what we have did, we do recall, finally we do convert the answer into least number of significant figure. If it is the least one is 1, so we do convert it into 2 for the reading or the measured value for the physical quantity. And for uncertainty, if it is having the 1 least count, least number of significant figure is 1, so we do remains 1 significant figure. Okay, so in the situation, the stress sigma in the wire is calculated by the expression sigma is equal to 4f over pi d square. Show that sigma is equal to 1.9n into 10 power 8, and they have given the values. The values they have given right here. D is equal to 0.40 millimeter plus minus 0.02 plus minus 0.02 millimeter, and F of the force they have given 25.0 Newton plus minus 0.5 plus minus 0.5 Newton. So these are the data given right here. So we have to solve, the sigma is equal to 1.9 into 10 power 8. So sigma according to the values 0.40 4f. F is 25.0 over pi is 3.14 multiplied by d square means 0.40. It's a square. In this way, sigma we can calculate it easily right here as 4 multiplied by 25 is 100 over 0.4 square, 0.4 square, 0.4 square, that is 0.16, multiplied by 3.14, so multiply by 0.16 multiply 3.14, that is 0.5024, 100. So 100 divided by 0.502, that is 199, and here we do have the diameter is in millimeter. We need to convert it, okay, because SI unit we need Newton per meter square. So instead of writing 0.4, we do write 0.4 into 10 power minus 3 meter. 0.4 into 10 power minus 3 meter, okay, plus minus we can write 0.02 10 power minus 3 meter, okay. So 0.4 multiplied by 10 power minus 3, 10 power minus 3, 10 power minus 3, it's a square, yes. So 0.4 square is 0.16 into 10 power minus 3, power with another power, that will be 10 power minus 6. So here we do have 10 power minus 6. Okay. After dividing it, we do have 199.20 multiplied by 10 power, this minus 6, whenever it shifts to the numerator it becomes 10 power plus 6, and whenever we do shift it to a standard scientific notation, after the one digit we do write the decimal, 1.99 into 10 power plus 8, and the SI unit will be Newton per meter square, okay. So keep in mind, whenever they have asked to write in the SI unit, so we must convert the given data into SI unit. Otherwise, the unit will be, if we do use 0.4 millimeter, then the unit will be Newton per millimeter square. Okay. Now, they have asked in the second part, determine the percentage uncertainty in the sigma. So percentage uncertainty we can easily find out. First we do calculate the percentage in F, percentage uncertainty in F. Then we do calculate the percentage uncertainty in D. Then we do calculate total percentage uncertainty in D square. And then we do add F and D square. So percentage uncertainty for the force, we have absolute uncertainty 0.5. We do write 0.5 over measured value 25.0 multiplied by 100%. So answer will be, that is 50 over 20. Okay, so it will become 2% because 0.5 over 25 multiplied by 100, that will become 50 over 25 means that 2%. So percentage uncertainty in the diameter, so we can use this data as well. We can use this data as well. We do have the same answer, not to worry about that, because units are being cancelled. This is the ratio, percent, 100%. Okay, So absolute precision is 0.02 millimeter. You can see that the units are being cancelled out. So either we will use 0.40 millimeter and with that 0.02 millimeter, or either we will use 0.02 into 10 power minus 3 meter or over 0.4 into 10 power minus 3. 10 power minus 3 is getting cancelled. So not to worry about that. But the unit will be same. So it becomes 2 over 40. 2 over 40, 2 over 0.4. 2 over 0.4 percent means 2 over 0.4. This will be 2 over 0.4. It becomes 5. 2 over 0.4, it becomes 5. So it means that this will be 5%. So percentage uncertainty in the case of d square, percentage uncertainty and d square means power factor. So the power factor is 2 and percentage is 5%, so it will become 10%. So percentage uncertainty overall in sigma, or the stress, will be the sum of percentage uncertainty in the F and the d square, because here the power factor is also acting right here, and here the division is being there, and the rule for the division and multiplication is we have to add the percentage uncertainty. So for the power factor, the total percentage uncertainty is 10% and percentage uncertainty in force is 2%. So overall percentage uncertainty, total percentage uncertainty will be 10% plus 2%, that becomes 12%. Okay. The second part that we have did, the third part, write the answer with uncertainty to appropriate significant figure. So appropriate significant figures, we do have the final answer. First we do calculate the 12% with this value, and then we will solve it further. So the answer for the sigma, that is 1.99 into 10 power 8 or plus 8 Newton per meter square, plus minus we do write 12% of 1.99 10 power 8 Newton per meter square. 12% means 12 over 100 multiplied by 1.99 10 power 8 Newton per meter square. So 12 over 100, that will comes out to be that will be 0.12 for the 1.99, 0.238 plus minus 0.238 into 10 power 8 Newton per meter square. And here we have to convert it. Now see the given data having 2 significant figures and 3 significant figures, so final answer will be converted into 2 significant figures. So 1.999 is more than 5, so we will add 1 right here, and it becomes 2.0. And don't get confused, it's 2.0. 2.0 into 10 power 8 having 2 significant figures. Okay. Now the final answer on the uncertainty, or absolute uncertainty, or the final uncertainty, we can write with appropriate significant figure. So we do see that how many significant figures are there in the uncertainty, absolute uncertainty. So here we do have one significant figure, and here also we do have 1 significant figure. So final answer must have 1 significant figure. So instead of writing this plus minus 0.238, we can write 2.0 into 10 power 8 Newton per meter square, and the last digit is 8, so 1 will be added right here, that becomes 0.24 and 4 will be simply dropped directly and we write 0.2 into 10 power 8, 10 power 8 Newton per meter square. In this way, we have the final answer.